Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. invideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. Today, we are going to start to understand how do we solve the KV cache memory problem. We learnt about the KV cache in the previous lecture, and we saw that it comes with a good side and it comes with a bad side. First, let me quickly recap what is the KV cache, why do we need it, what is its good side, and what is its bad side. So it all starts by looking at the inference pipeline of language models. And this is how language models do inference. We first have an input sequence of tokens. Let's say we have four tokens. The next day is, and then we have to predict the next token. That's the main task of language model inference. This input sequence goes through this entire architecture. It goes through this first block of data pre-processing. It goes through the transformer block. It goes through the output layer, and then we get a logits matrix through which the next token is predicted. One key thing to realize here is that to predict the next token, we only need the context vector of this last token. So let me explain to you how. Once we are in the multi-head attention layer, we get the attention score between this last token and all the other tokens. And that's how we can get the context vector for this last token. This context vector then goes through all of these remaining layers. It goes through these output layers, and ultimately we get a logits vector corresponding to is, which is the last token in my input sequence. This logits vector is a vector which has 50,000 tokens if, or 50,000 parameters if the vocabulary size is 50,000. And then I choose that index which has the highest value or the highest probability, and then I find the token corresponding to this index, and that's my next token prediction, which is bright. So the first key insight to remember during LLM inference is that to get the next token prediction, I only need the context vector of my last token of the input sequence. That's it. I don't need these other context vectors at all. That's the first insight. The second insight is that, let's say, uh, the next day is was the input and bright is the output. Now this bright is appended to my input, and that becomes my new input sequence. So the new input sequence is the next day is bright, which will again pass through this entire architecture and we predict the new token. So let's look at what happens when this new input matrix passes through the transformer block. Especially let's look at what happens when this new input matrix passes through the multi-head attention block. So here we see that we'll get the queries matrix, we'll get the keys matrix, we'll get the values matrix, we'll get the attention scores, we'll get the attention weights, and we'll get the context matrix. But if you pay close attention, look at these black boxes which I have marked. I have marked a black box over here. I have marked a black box over here. I have marked a black box over here, 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 and in the context matrix also. So the second key realization is that all of these black boxes are already computed in my previous iteration. In my previous iteration in the multi-head attention, I've already computed all of these queries, keys, values, except for this last row over here. That's corresponding to my new token. So I've not computed that. So the second realization is that I'm doing so many recalculations here. Can I store something? That's where the idea of the cache comes into the picture. So then we started backtracking to predict the next token. So what I have to do is to predict the next token based on these inputs, right? What do I need to predict the next token? I only need the context vector corresponding to the last token. So to get that context vector, what I only need is that I need the attention weights for my last token multiplied by the values matrix. To get the attention weights, I need the attention scores. To get the attention scores, I need the query vector multiplied by the keys. Now, all of these things which I have marked in the black boxes are cached, which means to get the keys matrix, I will cache my previous keys, I will cache my previous values, and I will only compute this new row. I will only compute these new rows. So whenever a new token comes in, all I have to do is that I have to find the query vector corresponding to the new token. I have to find the keys vector corresponding to the new token and append it to the cached keys. So that gives me the total keys matrix. And the third thing I have to do is I have to find the value vector for the new token and I have to append it for the cached values. Then I multiply queries with keys transpose. I get the attention scores. From that, I get the attention weights. I multiply it with the values matrix, and that's how I get the context vector only for the last token. This context vector for the last token will traverse the rest of this journey, and then it will predict my next token. So you see what we have done here. We don't recompute the values and the keys again at all. We store them from the previous iteration. That's the idea of caching. We cache the keys and values. Now, as we have seen in the previous lecture, what happens with caching is that it reduces the number of computations which we need to do. So if you see this line, when we implement caching, the amount of computations which we need to do increase only linearly with the number of input tokens. However, if you don't do caching, the amount of computations increase quadratically. So that's one good side of implementing k-value cache. The good side is that it reduces the number of computations which we need to do. That ultimately reduces our cost. That's a good thing for us. Then what's the bad side? The bad side or the ugly side of the k-value cache is that or the key value cache is that we are storing something now. We are caching something. And just like every piece of land, to own every piece of land, we have to pay a price, right? Similarly, for every piece of data stored in the memory, for every single parameter stored in the memory, we have to pay a price. The number of parameters you need to store when you look at a key value cache is given by this much. Why is it this much? Well, because let's look at one transformer block initially. If you look at one transformer block, let's say I have four tokens. The next day is, let's say this is my four tokens and each token has a dimension of 4. Now these dimension is the number of attention heads multiplied by the head dimension, so that's n into h. The number of rows over here is equal to my context size, so that's s. And this is just one batch, but if I'm processing in multiple batches, then this will be multiplied by b. That's where the b into n into s, h into s comes in. These are the number of parameters which need to be stored. And remember, if this is the keys, uh, if this is the keys matrix, there will be a values matrix along with it. So then this will be multiplied with 2. And then I'm just showing this for one transformer block. There are usually multiple transformer block in language models. So that will be multiplied by L, which is the number of transformer blocks. And this one more 2 additional is the number of bytes per floating point. So I'm assuming that each parameter stored is 16 bits, which is 2 bytes. So the size of the KV cache is given by L into B into N into H into S into 2 into 2. Now, if you have GPT-2, that's 36 MB of memory. If you have GPT-3, that's 4.5 GB of memory. But if you have DeepSeek R1 or their V3 base model, which essentially has 61 transformer blocks, 128 attention heads, and each head having 128 dimensions, context size of 100,000, the KV cache size is 400 GB. That's a huge size. Now, what happens with this huge size is that your memory is overloaded. And for remember, for every piece of memory occupied by data, you have to pay a price. So that would increase our price during inference because the company running this also has to incur more cost. So this is hugely disadvantageous to us. The more memory which is stored, our overall computations will also become slow. And the thing is, as the parameter size increases of the model, right? So here, as I go from left to right, the model is becoming more and more complex. As the parameter size of the model increases, the size of the k value cache just goes on increasing. That's actually shown by this red curve over here. So key value cache speeds things. That's the good side, but it takes space. That's the dark side or the ugly side. I hope in this much time I have provided a summary of what the key value cache memory problem really is. So the memory problem needs to be solved because of course we cannot have 400 gigabytes of memory being occupied all the time. That would slow computations, that would cost us more as a company, and so I'll charge my clients also more. DeepSeek costs very less during inference time. So of course they did not go with this directly. They made a number of innovations, and their main innovation is the multi-head latent attention. But to get to that, we first need to understand innovations which came before that. And the first major innovation which came before that is the multi-query attention. So in the rest of this lecture, we are going to visually understand the multi-query attention, its advantages and disadvantages, and then we are going to implement it in code. So let's get started. The way I think about multi-query attention is that what is the simplest thing which you can do to solve the KV cache memory problem? And multi-query attention solves this problem by asking the question, what if all the attention heads share the same key and the value matrices? So if you just look at this statement, it feels difficult to visualize this. Okay, what does it mean attention heads sharing the same key and value matrices? So I've constructed some visuals for you to understand this a lot better. So first let's look at normal multi-head attention without multi-query attention. In normal multi-head attention, we start with an input embedding matrix. Let's say I have 5 tokens. The next day is bright. Each token, let's say, has 8 dimensions. That's the embedding dimension. We multiply the input embedding matrix with the keys and keys trainable weight matrix and the values trainable weight matrix. Now, if you look at the keys weight matrix, let's say there are 4 heads. If there are 4 attention heads, the keys weight matrix is split into 4 parts. The first is the keys weight matrix for attention head 1. The second is the keys weight matrix for attention head 2. The third is the keys weight matrix for attention head 3. And the fourth is the keys weight matrix for attention head 4. That's the similar for the values, or that's what happens for the values weight matrix also. The first part or the first split is for the first attention head, second for the second head, third for the third attention head, and the fourth for the fourth attention head. Now, normally in normal multi-head attention, you see I have shown all of these head colors with different values, right? This is shown in a different color. This is shown in a different color. The reason I have shown in different colors is because naturally the weights of the keys for different attention heads are different. Why would they be the same? They are initialized in random manner. Similarly, the weights for, let's say, for this attention head and for the second attention head, the values weights are different from each other. And that's why all of these are shown in different colors. And naturally, now when you take keys weight matrix and values weight matrix like this and multiply it with the input embedding matrix, you get the keys matrix and the values matrix, right, for different heads. And here also, since the WK and WV are different for every attention head, the final keys matrix is also different for head 1 compared to head 2, compared to head 3, compared to head 4. And the final values matrix is also different for head 1 and head 2 and head 3 and head 4. Now, if you see very closely the number of dimensions in the key value cache, the number of dimensions of the key value cache is directly dependent on the number of attention heads which we have. And every head will have a certain dimension, right? So if let's say, uh, take a look at this keys matrix. And if it generated during one iteration of my inference, I will have to cache this entire keys matrix. So that means I have to cache the keys matrix for head 1, I have to cache the keys matrix for head 2, I have to cache the keys matrix for head 3, and I have to cache the keys matrix for head 4. What multi-query attention does is that it says, what if I have to cache just the keys for one head and I don't cache the keys for the other heads? Then you might be saying, okay, that will not work because all of these other heads have different values. You need to cache them. Multi-query attention then says, what if all of the attention heads have the same values as the head number one? So if you look at the keys matrix, what if head 1, head 2, head 3, and head 4 all have the same values, such as like this? If you look at the values matrix, what if head 1, head 2, head 3, and head 4 all have the same values, such as I'm showing right now? So that actually means that if you look at the trainable keys matrix and trainable value matrix, here also head 1, head 2, head 3, and head 4 will have the same values. So among these different heads, the values are same. That's why I've shown it with the different color. Within one particular head, the values can change. But if I showed them with a different color, it would be too many colors. So that's why, for the sake of simplicity, within one head also I've shown with the same color. But the real point I'm trying to illustrate here is that for head 1, whatever the values are there for head 1, it's the same for head 2, head 3, and head 4. And that's exactly the same for the values weight matrix. Whatever values we have for the head 1, it's the same for head 2, head 3, and head 4. Then if you think about it, then I just need to cache it for one head, right? I just need to cache the keys and the values for one head. I don't need to cache for all the other heads because they are the same values. So why should I store more things in my memory if all of these head 2, head 3, and head 4 are the same values? So that's why what happens in multi-query attention is that if you look at the size of the KV cache, it depends on the number of attention heads, right? Now this is taken out of the picture completely. This is taken out of the picture completely because we get rid of the differences in the heads, which means that now I only need to store the keys and the values for one head. So in the case of multi-query attention, the size of the KV cache size or the size of the KV cache suddenly reduces by a factor of n. And if you have 32 heads or if you have 128 heads, like in the case of DeepSeek, DeepSeek has 128 heads. So multi-query attention reduces the KV cache size by a factor of 128. That's a huge reduction. That much is the reduction in the memory space if you use multi-query attention. So let me revisit what I just mentioned. What I just told you is a simple trick. I told you that instead of having different WK and WV values for different heads, what if you just have it for one head and then you create copies for head 2, head 3, and head 4? So if you create copies in WK and WV, even in the keys matrix, what will happen is that you just get the keys matrix for head 1 and you create copies for head 2, head 3, and head 4. So even if you create the values for head 1 and you create copies for head 2, head 3, and head 4, that is what is actually meant by what if all attention heads share the same key and the value matrices, right? Now what this ultimately leads to is that it leads to the fact that the size of the KV cache reduces by a factor of n because I don't have to store the keys and the values for all my heads right now. I just store it for one head. That's it. And then when the time for inference comes, I just use the same values across different heads. That reduces the KV cache size. Now, one thing to keep in mind here is that the queries, if you look at the query vectors for the different attention heads, Q1, Q2, Q3, and Q4, those are different. I am just saying that in multi-query attention, the keys and values share the same values across heads. But if you see for head number 1, for head number 2, for head number 3, and head number 4, I have marked the query vectors with different colors. The reason I have marked them with different colors is because they are different. I am not making the queries same across different heads. If you at any point you get confused how to interpret the rows and the columns here, just remember that in the queries keys and the value matrix, the rows are my number of tokens. The next day is bright, and the column Columns are my total dimensions, which were 8, but now they are just split into 4 attention heads. So each attention head will get a dimension of 2. The queries, so each query still has its own values, like in multi-head attention, but the keys and the value vectors are the same across the different heads. Now think about this for a moment, right? If you are reducing by a factor of n, DeepSeek has 128 heads. So multi-query attention reduces the KV cache size from 400 GB, which we had calculated earlier for DeepSeek. Remember, the KV cache is 400 GB, and now it's reduced by 128 to 3 GB. That's incredible, right? That's a huge reduction in the KV cache size. So then you might be thinking that, wow, this is great reduction. So why doesn't everyone just use multi-query attention? Because multi-query attention also comes with a dark side. And I want you to pause this video for a moment here and think about what the dark side might be. The hint which I'll give you is, think about why we started doing multi-head attention, right? What is the advantage of multi-head attention, and what are we losing out by essentially doing multi-query attention? Okay, so let me give you the answer. If you think about why we started multi-head attention, the main thing which we wanted to capture was different perspectives through different heads, correct? So let's say if you have a statement like this: the artist painted the portrait of a woman with a brush. It can be either something like this: the artist painted the portrait of a woman using a brush, or it can be something like this: the artist painted the portrait of a woman with a brush in her hand. It can be either of these two. If you just use the self attention mechanism, it can only capture a single perspective. It cannot capture multiple perspectives. And that's why we had started understanding multi head attention. So remember the purpose of multi head attention. The purpose of multi head attention was, since the queries, the keys, and the values are split into multiple heads, ultimately we'll get uh, an attention weights matrix for head 1, we'll get an attention weights matrix for head 2, then we'll get a context vector matrix for head 1 and head 2. And ultimately, when we merge these two context vector matrices, the first attention head will capture one perspective, my second attention head will capture another perspective. So the idea of having different attention heads was to capture different perspectives. Now, if you suddenly say that my keys, my K1 and K2 will be the same, that's what you're saying in multi-query attention, right? You're saying in multi-query attention that my K1 and K2 will essentially be the same. They won't be different values. My V1 and V2 will be the same. They won't be different values. What that does is that reduces the amount of different perspectives which we can capture across these different heads. So that means the performance of our language model won't be as good as it was with multi-head attention. The power of multi-head attention was that K1 and K2 were different, V1 and V2 were different. So we had given the each attention head the provision to capture something completely different. But now, if you are making the keys and the values same across all the attention heads, then you are restricting the power of the heads, right? You are restricting the diversity which different heads can capture, because they all share the same keys and the values. Although the queries they share are different, so the attention scores will be different. That's fine, but still you are keeping the keys and the values to be the same across different heads. So you are kind of restricting the amount of diversity which you can capture through different attention heads. That's one of the huge drawback of multi-query attention. Although it is saving my memory, it is, we get a significant performance degradation, and that is not what we want. DeepSeek models are hugely performative. They are great at performance. They are great at capturing context. So of course, this is not what DeepSeek implemented. That's the main disadvantage of multi-query attention. Because we use the same keys and the values across different heads, we get a severe performance hit. Memory is saved, that's good. So we counter the dark side of KV cache, we save the memory, but MQA introduces its own dark side, and we get a severe performance degradation. What I'm going to do right now is that after this point, I hope you have understood the concept of multi-query attention, its positives and its negatives. I'm going to now take two models, two language models. one which implements multi-head attention, one which implements multi-query attention. They are already pre-trained models, and we are going to visualize the key value matrices in these heads. We are also going to compare the inference performance of these models. So let's get started with that now. All right. So the models which I'm choosing for this comparison is that we are choosing a GPT-2 model which implements standard multi-head attention, and we are going to select the Falcon model. So if you search Falcon LLM, you will see that Falcon is a series of language models which are pretty popular. They are open source models available through Hugging Face, and we are going to use that variant of the Falcon model which uses multi-query attention. So if you see, I'm going to code right now. I'll share this file with you. We are going to use the GPT-2 medium model for our multi-head attention purposes. That's a 355 million parameter model. And we are going to use a Falcon 1 billion parameter model, which uses multi-query attention, which means it uses the same key value matrices across all the heads. Now, I'm running this on an A100 GPU, but if you're on Google Colab and if you don't have access, if you're on Google Colab and if you don't have access to the A100, that's completely fine. You can just go to the runtime and you can just switch to a T4 GPU, which is free, and the code which I'm sharing will still run. So these models are pre-trained. I'm just loading these models from Hugging Face, and then I'm using this prompt: the quick brown fox jumps over the lazy dog. Okay, I'm using this prompt. And so first, in the step one, what I'm going to do, I'm just loading these two models. So here you'll see the loading has completed. So this took around 3 to 4 minutes for me on A100. On a T4 GPU, it might take 10 to 15 minutes. And overall, you will need to allocate around I think throughout this full exercise, you will need to allocate around 5 GB of space. That's it. Then what I'm doing is that I'm actually I'm passing this prompt through this entire model, and I'm evaluating the time it takes for the model to give me the attention scores essentially. So I'm evaluating the time it takes for my input prompt to pass through the entire model. Now remember that uh, multi-head attention, we are using separate key values per head, and multi-query attention, we are sharing the key values across all the heads. And multi-head attention, the memory consumption is higher. Multi-query attention, the memory consumption is lower. Why is the memory consumption lower in multi-query attention? Because we reduce the number of heads. So remember the KV cache size formula for multi-head attention versus multi-query attention. For multi-head attention, it's this. For multi-query attention, we reduce by 1 by n. So we get rid of this number of heads. So for multi-query attention, we expect to reduce the memory consumption. So overall, I would expect a good performance time in my multi-query attention because I'm saving less amount in the memory, and I expect that to improve my performance. And I'm also doing less number of computations actually because I'm sharing my same keys and values across different heads. So if you run this second code to compare the inference times, you will see that the inference time for multi-head attention is 1.062 seconds, and the inference time for multi-query attention is 0.64 seconds. So that's, I think, almost a factor of 40% improvement in the inference time. Why is there a improvement in the inference time for multi-query attention? Because we are saving less in the memory, since we reduce the number of heads in the KV cache formula, and we are also doing less number of computations since the keys and values are just repeated across multiple heads. I am not going through this code because my main intention is not to walk you through this code, but to essentially show you how these models function and what we can diagnose from these already pre-trained models. The next thing which we are going to do after this point is that we are going to evaluate the trainable key matrices and the trainable value matrices for these models. So let me go to the top here and let me show you what we are exactly going to visualize. We are going to visualize this. So what you will see is that, so I'm going to visualize, this is WK, right? And this is WV. So for the multi-head attention, we are going to first see matrix for head 1, We are going to visualize the matrix for head 2. We are going to visualize the matrix for head 3. We are going to visualize the matrix for head 4. Each of these matrices would look different from each other because in the multi-head attention, we don't share these values. And we are going to visualize the same thing now in multi-query attention also in our code. We are going to visualize this head 1, this head 2, this head 3, and head number 4. So in the visualization, you will see that. So let me show you directly the visualization. Again, I won't take you through the code. So this is the GPT-2 medium visualization. So let's first see for head number 0. This is the trainable matrix for head number 0. It is the same thing as the first. Let me go over here. It's the same thing as this first head trainable weight matrix, but let's see the dimensions here. The number of columns here are equal to 64. Why? So if you see 0 to 4, it goes up till 64. The number of columns are 64 because the head dimension is 64. Here the head dimension was 2, but now this is just 64 in our example, and the number of rows are 50. So the number of rows here are actually equal to the number of embedding dimension, and the embedding dimension is I think 1024. So we cannot show all the 1024 here, so I have just shown 50 rows over here. So that's why it's 50 rows and 64 columns. 64 is the head dimension and 50 is just a choice I have made because I can't show the entire 1024 rows. So take a look at this heat map. So every color here represents one value. This is the heat map for head number 1, heat map for head number 2. Head number 0 and head number 1. You will see that the heat map differs from head 0 and head 1, right? It differs from head 1 to head 2. So you'll see that all the keys have different heat maps over here, which is expected since the keys don't share the same values. Even the value matrices. So now I'm plotting the value matrix for head 0, value matrix for head 1, for head 2. They all seem to be very different from each other. Now you will see for the Falcon model. This is the key matrix which has been plotted for head number 0, which means that this is the trainable key matrix which is plotted for the first head right now. And now if you scroll down below, you'll see that the values for head 0, for head 1, for head 2, for head 3, for head 4, for head 5, they are all the same. Because all of these heads now share the same key values. Similarly, if you go to the value matrices, you will see that for head number 0, for head number 1, for head number 2, for head number 3, for head number 4, and for head number 5, all of these heads share the same value matrices. Why do they share the same value matrices? Because that's the main thing which is implemented in multi-query attention. The same weight matrices are shared across different heads. That's the key advantage of multi-query attention. So I'm just visualizing it here for you. This is the second visualization I wanted to show. For GPT-2, the values are different across different heads. And for Falcon model, the values are same across the different heads. The last visualization is I want to show you the attention score matrices. So first you can see for multi-head attention, I'm just looking at the last transformer block. Remember there are multiple transformer blocks. And if you see in each of these, I'm showing that. So now if you see, I have the quick brown fox. The quick brown fox jumps over the lazy dog, right? So there are 9 tokens. So the attention score matrix will be 9 by 9. Let me write it on the whiteboard over here. The quick brown fox jumps over the lazy dog. The quick brown fox jumps over the lazy dog. So this is the attention score matrix for the first head. Similarly, there will be an attention score matrix for the second head, etc. I have just shown these values over here. I have just shown these values over here for the different heads. You see, that's what this heat map actually indicates. So GPT-2 has 16 heads, I think. GPT-2 has 16 heads, and you see this attention score heat map for all the 16 heads. You'll see that it's different from each other. And then for Falcon, I've shown the same thing, but Falcon model has actually 32 heads. So for each head, I've shown the attention score heat map, which is 9 by 9 because there are 9 tokens. And here what I actually want to point out is that the main advantage of multi-head attention is that each head can capture a different perspective, and each head does capture a different perspective. So ideally you should see more diversity in what all is captured through these different attention heads. Whereas if you see the Falcon model, right now it looks kind of similar, but overall the effect is that the diversity captured by each head is not that high because the keys and the values among these different heads are shared. So that's what I wanted to show through these plots, that for the Falcon models, if you see for the different heads, the diversity for many of these heads is not that high. They look almost kind of similar. This effect is not that pronounced in this visualization right now, but this highlights one main disadvantage of multi-query attention. And the disadvantage is that the diversity among different attention heads is not that much. So we don't capture as many perspectives. So our model becomes weaker. Our model does not perform as well. All right, so this brings us to the end of this lecture on multi-query attention. Multi-query attention is the first method which people or researchers invented to solve the KV cache memory problem. And the idea is that we share the same key matrices and value matrices across all the heads. Similarly, we share the same key weight matrices and value weight matrices across all the heads, and that reduces the KV cache by a size of n. So for GPT-3, if the KV cache took 4.5 GB, since we have 96 attention heads, for if you use multi-query attention, there is almost a factor of 100 difference reduction in the amount of memory needed. DeepSeek has 128 attention heads. So multi-query attention actually reduces the KV cache size by a factor of 128. So from 400 GB we go to 3 GB. That's the good side of multi-query attention. The dark side of multi-query attention is that it defeats the purpose of multi-head attention. The main purpose of MHA was to capture different perspectives through different attention heads. In multi-query attention, this purpose is defeated because well, although different attention heads value will be different because the query vectors are different across the different heads, but the keys and the value vectors are exactly the same. So we cannot capture as much diversity. So the model performance will degrade. The language model will not be as good in capturing the complexity of the underlying sentences or the paragraphs. In the next lecture, we are going to look at another method to solve the KV cache problem, and that's the grouped query attention. We'll also see a code for the group query attention, and then finally we'll move to the multi-head latent attention, which is the key innovation in the DeepSeek paper. Thanks a lot, everyone. I hope you are liking these lectures. Please make notes. Now we are getting deeper and deeper into the DeepSeek innovations. So as we get deeper, when you follow along, things might get a bit challenging. So make notes. You can share the notes with me, ask doubts, etc. Thanks, everyone. I look forward to seeing you in the next lecture.